2.4, complex numbers. Complex numbers are things that do not go on the number line. So real numbers are stuff that goes on the number line. So square roots are just fine on the number line. Decimals are just fine. And of course, integer values are just fine on the number line. Imaginary numbers look like this. They have a negative inside the exponent, inside the square root. Because of that, you can't place them on the number line. In fact, we do have something called a complex number system. We have complex numbers that go like this. Real numbers go on this side, and complex numbers, a little symbol for, oh, did you guys even know? Here, for real numbers, there's a symbol for real numbers. They go like this. It's like this little double thing and like an R. Those are called the real numbers. Complex numbers are like this, like a C with a little extra little line through it. So we do have that right there. So complex numbers are not on the real number. They actually are somewhere in space. We think about them as off of the real numbers, but having their own presence. So we think of them as like Y values off of the number systems that we have. And it was kind of crazy. Here's my thinking here. Oh, Dylan, go ahead. Question?
So, like, say you're trying to express an imaginary number on a number line, or like on a graph. With that graph, like, would there be a way to do it without like dealing with different dimensions of the graph?
Yeah, in this way, this right here, like if we were to graph 3 plus, which is a little beyond the scope of this class here. So 3 plus 4i, here's your real part. Here's your complex part. We're going to graph it as 1, 2, 3. 1, 2, 3, 4. We're going to graph it right here. Again, it's not an XY grid. Don't think of it as XY because that's real numbers to real numbers, right? This is going to be real numbers to complex numbers. And another fun trivia set is, how many of these graphs do we normally use? In fact, I would say normally use. We have the X and Y grid, right? Now we have the real and the complex grid. Then we have the angle and distance grid. That's another one we use in trigonometry called polar coordinates. Okay? So by the time we stack it all together, normally, generally in life, we got the three-dimensional grids, right? Real, three-dimensional, real, and complex. So by the time you end, you're looking at, we normally use about 12 or 13 different grids in life.
We've only learned one.
We've only learned one.
I mean, yeah. Like there's polar coordinates.
Yeah, polar coordinates is a third one, yeah. So yeah, we have quite a bit here. Okay, another fun little fact is this right here. In 250 BC, when Pythagoras was on the scene, we figured out that we actually need square root numbers. Square root numbers were not really known until then. Well, before then, with the Egyptians and going all the way back to earliest civilizations, we find out in earliest civilizations, they did use fractions. Egyptians, for some reason, used unit fractions only. They thought of like one piece out of something, right? So they would write 1/10, or they would write 1/25. They would never put an extra number on top. So their Egyptian number system, let's say you wanted a fraction that involved like 3/25, right? So they would write it as 1/25 plus another 1/25 plus another 1/25. They would never write 3/25. And for more complex fractions, because they only had certain denominators. So what they would do is they would have just some funny. They would write something like this. Right here, right? What fraction would that represent? So the Egyptians would write 1/3 plus 1/4 plus 1/5. And that would be the number. That is the number that is needed for solve this equation, sort of thing. If we think about it, let's see, this is now, what, 60, I believe? Complex number 60, 60, 60. That's going to be 20. That's going to be 15, I believe. That's 12. Right, times 3, times 15, times 12. That's 27, 47. So 47/60ths. They would write it as this right here. Interesting. But anyways, fractions, we find out early civilizations, Sumerian civilization, Babylonians, Assyrians, they used fractions. And it wasn't until the Greeks that we actually had to say, whoa, fractions are not enough in our world. When you look at, when you look at the square, that's a 1 by 1 square, and you take a diagonal across like this. That value there is going to be square root of 2. Agreed or disagreed by Pythagorean theorem? And so they didn't have that. They didn't have square root of 2. So what they were trying to do is they're trying to say, okay, what fraction A over B would give me C squared? That was their sort of thing. And then the person that discovered it, the fact that this guy can't be a fraction, he came up, it was a weird system. So Pythagoras, he had his own school developed, right? And it was like a math school, and it became a mystical school as well. It was this sort of like world of numbers, and only certain secret society people can get in. And so when they discovered this, the fact that that square root of 2 cannot be a fraction, that's not possible. He broke the number system of the decades. Are we good? Kind of like Ralph broke the internet. He broke the number system. So what happened was he started saying, like, look, we don't have enough numbers. There's actually something else here. And so everybody's discarding him. Like, no, you're wrong, you're wrong. And so he goes sailing on a ship. The ship itself is wrecked at sea, dies, and they say the gods just killed him because he destroying our number system life. And so it wasn't until a little bit later, but eventually about 250 BC, we discover we need square roots to make sense of our world. We good? And we thought at this point, we're done. We don't need any other numbers to do stuff. And Dr. Cardano, playing with numbers and the quadratic formula, he comes up with this idea that we actually need negative numbers inside a square root. Because imagine, that's kind of weird, isn't it? Just like 500 years ago, we developed a whole new number system. And it wasn't until late 1800s that we found a use for it. First, it was just theoretical. Dr. Cardano just said, I'm going to start writing negatives inside my square root. I'm going to say those are answers. And late 1800s, with the development of electricity, we find out, oh, wow, look at this. This math fits perfectly into electrical engineering, into how electricity works, all that good stuff here, which is, I think, pretty cool. So really, about only 200 years ago, we needed a whole new number system to develop. So I'm thinking to myself, you know, if we invent space travel, right? And is there such thing as hyperspeed? I'm not sure. Let's see. But will there be math that's needed for that piece? I'm not sure. Let's see. Okay, anyway, so back to, yes, Dylan.
Throwing off what you're saying about space travel, I think tomorrow actually SpaceX is testing Starship, which is supposed to be in the future what is going to carry passengers to Mars, I'm pretty sure.
Oh, wow.
It's a one-way trip
That's
to Mars.
Oh, yeah.
They're just testing it tomorrow?
Yeah, I'm not sure if it's actually going to be the Mars shuttle, but it's in the future when space travel is more normalized, it can carry up to like 100 passengers.
Whoa, interesting. Okay. Wow.
It looks like a tin can right now, but it's apparently like off of the line, the most advanced shuttle we have in the world.
Gotcha. Okay. All right, class, let's go. Let's keep on going here. For Owen, the definition of I, the imaginary number, is square root of -1. So then what we do is if we square both sides, we get this. It's not a definition, but we're going to use this quite a bit. Whenever you see I squared, the simple form is just write a -1. So I squared will always be reduced down to -1, kind of like we would do with fractions, right? 6/8 becomes 3/4. So there's your two things to write down if you haven't written down to memorize them. So there's that. Next. So we have imaginary numbers. That's what these guys are right here. Then we have real numbers. So if we put them together as one big unit, we have the complex numbers. And complex numbers are written like this. They're written as A plus B. So we have the real part, then we have the imaginary part, stick them together, you got the complex number. I think
So
makes sense.
It's just A plus B or
A plus BI with a little I next to it. So it's examples 3 plus 4I would be example of a complex number. Here's your real part called 3, imaginary part called 4I. We stick them together, complex number, done. Okay, so let's take a look at some properties. We have to learn how to add, subtract, multiply, divide.
So, the imaginary number with a real coefficient is still imaginary number.
So if I just wrote down 3i, for instance, right? I could think of that as just an imaginary number, or I could think of it as a complex number with the with the real part being 0. So that's why the definition sometimes is like, oh, the complex number 3i. They're understanding that's just the overarching things. Okay. Cool. Next is what we did is we wrote down numbers in complex form. So in this case, you see a negative inside a square root, that becomes an I. The 16 itself is still a square root of 16, which is 4. Are we good? Thank you so much. All right, and in this one, you see an I squared, and what you're going to do is you're going to reduce that down to a -1. Still a complex number, and everything's fine. This one, yes, you can think of it as a complex number. You can think of it as an imaginary number. It's interchangeable. Okay, we're good there so far. That's from last time still. So every good complex number? Jamming, let's go. Then how do you know if two complex numbers are equal to themselves or equal to each other? With the real numbers, we never think about that, because with the real numbers, if you say x is equal to 17, you're done. Right? You can almost think about it this way. We're kind of solving this. We're saying, hey, look, if x plus 2 is equal to 10, what does x have to be for this to be true? 8, right? You're kind of like, oh, you know what? It has to be 8. You're kind of doing a little algebra in your head. So the question here is this: if a plus bi is equal to 7 plus 3i, what would a have to be and b have to be for this complex number to be the same? Obviously, a has to be the 7, b has to be the 3. Does it get more complicated? Of course. You can say a plus 6 plus 2bi is equal to 6 minus 5i. What does a and b have to be in order for these two complex numbers to be equal to each other? Well, we're going to have to take the real part, set it equal to itself, solve. So a would have to be 0, and look at the imaginary part, set these guys equal to each other, solve, and then b will have to be -1. So there's the a has to be something and the b has to be something in order for these guys to be the same. I could even go over here and say, look, what does a have to be for this to be equal to each other? And it's 8, right? So same thing here. We only do it once for real numbers. We've got to do it 2 different ways for complex numbers because there's 2 pieces to it. Okay, enough of that. We good? Let's jam. So can you perform the indicated operation in exercise 3? If you want to write down the... So here we go. Add, subtract, we're going to look at add, subtract, multiply, but divide is going to be kind of unusual. That's going to be a little extra piece here. So perform the indicated operation. Let's go. So we're going to add 2 complex numbers to each other. We're going to subtract 2 complex numbers. And of course, have to add in some decimals and stuff like that. Boom. Oh, and then let me change to darker color.
Let's say 3/4.
3/4 on the first one right here? 3/4, All right, so what do we do here? Well, we can't interchange the complex and the real, or the imaginary part and the real part. So all we do is we add the real parts together, which is this right here. And we add the imaginary parts together. So that one and that one. In fact, let me make that into a. So the I stays with the I's and the real numbers stay with the real numbers here. So 13 minus 5. 8 is good by me. Negative 2I plus 6I. Boom, and I'm good to go. There it is. I've just added two complex numbers and I'm good to go. All right, if you have the subtraction symbol, the only thing is if you think about subtracting in your head, that's fine. Most students, what they would probably do, they would drop all the parentheses, just like we do with polynomials. This guy becomes negative 6. This becomes plus 13I, and then you can simplify it down.
Is it -3 plus 15?
Oh, go with that. Cool. Okay, and then all yours for the fractions. That one's going to involve a little bit more work. Abe, do you have it already? Cool.
Is that 7 over, what's the denominator there?
8, right?
Is that 8?
Oh, that's 8.
8, oh, yes, that's 8. Yeah.
Which is a 1.
Gotcha. So on this one, probably need to do off to the side, right? Because you're gonna have to do 3/4 plus 2/3. So maybe off to the side here, 3/4 plus 2/3. Wow, common denominator is 12. So that's 9, 8, 17. I like that. 17/12. Okay, the next one here, negative 5 halves minus 7/8.
Oh, I said negative? Oh, yeah.
Let's see, common denominator would be 8. Boom. And Abe, what'd you get?
Minus 27 over 8.
Awesome. And did it correct. Okay, guys, are we good there? Keeping up there? Okay, next. Okay, good. Easy enough here. It's easy enough because that's simple. Could you imagine like when we do we calculate amps or ohms inside an electrical circuit? That's exactly what we do right here. A little more complexity. Okay, so let's jam here. Next one is right the complex conjugate. Whoa, we have something called the conjugate. First things first, what in the world is a conjugate? So maybe write it like this here. A plus conjugation is different. Yes, Conjugation. Conjugate the verb. That's when you say like that's right, something like that, yeah. I ate, you ate, she ate, he ate, they ate.
So what is the complex conjugate?
Perfect, Abe, you're totally right here. So complex conjugate says the two numbers in front, the real numbers are exactly the same. Complex, imaginary numbers in the back are exactly the same, except for the sign in the middle has been changed. The changing of the sign. So these two are complex conjugates. And something interesting comes out, which we kind of already saw here. So if you can write for me the complex conjugate of this number here, and after you write it, let's multiply those guys together. So 1 plus 2i, the complex conjugate would be 1 minus 2i. That's it right there. But then let's take the time to multiply these guys out. So this times this is what I want. And something interesting is going to happen. Let's say something just disappeared on us, and that's a cool thing. So FOIL method, here it is. 1 times 1 is 1. 1 times negative 2i is a negative 2i. 2i times 1 is a positive 2i. And let's see, 2i times a negative 2i minus 4i squared. That's cool. Thank you, Charlie. Go ahead.
Because if I squared equals -1,
Oh, that's right. Yeah.
it's +4.
Yeah. So hold on. Let's get rid of these guys. First of all, the i's are gone. Is that right? And this becomes, let's do it in steps here. This becomes -4 times -1, which becomes 1 plus 4, which becomes 5. Whoa, that's interesting.
So, are we going to treat all, imaginary numbers just as square root of -1 by default?
The symbol that we use for it is just I. So yeah, this guy right here, technically in our mind is, I'll place this little bubble, cartoonish bubble. We think of that's what's happening right there. It's square root of -1 sitting there. We just use the symbol I. So we don't have to write square root -1, square root -1 all the time. Because mathematicians are technically like lazy. Like, why use less symbols?
Great math.
Abe, looks like your field, man.
Dave, I think you're just too.
Okay, so real quick here, Owen, since the i's disappeared, notice there's no I in here. Isn't that a real number?
I mean, yeah, but you can also say +0i. and
You
it's
could, yeah, Except look what happens here. These i's all disappear, and the I squared is going to turn into -1, right? So what we did is we went from a complex number, and we ended up with a real number. Are we good? Awesome. That is exactly what multiplying by conjugates does, because the signs in the middle will cancel out these two middle terms like we do with polynomials. And we are done. We got ourselves a real number. Okay, another one here. Oh, let's see. I think I need to. So B. B is, let's go with it. 4 minus 3i. All yours for this one. Try it yourself. See what you end up with. While you're doing that, I'm going to add an extra slide here real quick here. Okay, 4 minus 3i. Okay.
Why do you think you did something wrong?
All right, we good? So off to the side somewhere underneath it, whatever you like here, but just kind of put down the complex conjugate. That's it right there. And then from here, off to the side of the sheet of paper, then we are going to multiply this out. And eventually you should get just a regular number, a real number. If you don't, you did something wrong. All right, I'm gonna go for it here. So 4 times 4 is 16. Oh, hold on. Really, do I even need to do the middles? No. Why do something if I don't have to do it? Okay, so then boom, another lazy. No, I would not say lazy. How about this, Abe? More efficient way. How about that, right? More efficient way of doing it. -3. Let's do it the fast way here. -3 times 3. -9, but you know you're gonna have an I squared there, right? So can we just put +9 already?
You're right.
Cool, and that just makes 25 a whole bunch easier. We good? Okay, so let's do this.
So that complex conjugate will always be a minus b squared.
Complex conjugate will always be a opposite sign bi. So it's always opposite sign. That's the complex conjugate.
Oh, sorry, multiplying a complex conjugate by the original complex number.
Oh, perfect. Let's go over here now. Yep. So let's do like a quick little formula. Thank you, Dylan. A plus bi multiplying a minus bi. Those are complex conjugates, right? What we're going to do here is we're going to have a squared. Talk to me if this makes sense. A bi times a minus bi should give us a negative b squared, right? I squared.
I'm just gonna give you a positive b squared.
So it gives us this initially, right? And then eventually this is going to give us this right here. So Dylan, absolutely right. Here's our formula. So then let's do the next one. Let's do it by formula. I'll just be
So we
quick
don't have
and
to
done.
go through the step of the negative bi squared.
Yeah, so we don't even care where the numbers are. We're just going to take this a, whatever it is, we're going to square it, take the b, whatever it is, square it, add them together, and done. Which is kind of what we did right over here, really, right? We took the 4, squared it, took the 3, squared it, added them together, and done. All right, so 2 plus 3i, all yours there. All right, writing the complex conjugate, 2 minus 3i, there's your complex conjugate. When I multiply these guys together, I get 4 plus 9, which is 13, done. Are we good? Okay, everybody good there? Is that a fast way of doing it? Tristan, question or just stretching? Yeah, good.
And the test question, do I say?
Now,
Yes, one of them will be just like this.
only one.
Just one. Okay, next one. Are we on what, example number 5? Okay, this one now gets a little bit trickier, but still, we're cool like that. You guys are smart. Okay, write the quotient, Quotient, in standard form. And quotient just means, yep, it's a fraction, one over another. So whenever we talk about a quotient form for whenever we talk about standard form for a quotient, real quickly here, is it's a reduced form, right? You think of like 3/4. 3/4 will be standard form because it's reduced, you can't reduce it anymore. It's simplified as much as it can be.
Couldn't you get 1.5? I think simplified it. That was next time.
Yep, okay. So what makes it more complex if you had something like this? If you had something like this, could that be reduced? Yeah, that square root of 16 becomes a 4, right? Okay, so what we say is this. We say we don't like any square roots in the bottom. Because those should be able to be simplified some more. Now we could have square roots on top, because on top, remember, you can have zeros, you can have whatever you want on top. And so we have this. Oh, hold on. So if I had something like this, how we simplify that.
Multiplied by negative squared and negative 16 over c squared negative 16 as a form of 1. And then we have 3 squared.
Or just 3/4i.
Okay, that's cool. How about the 16 becomes a 4, but because it's a negative 16 becomes an I. We have ourselves a little problem. Do we still have, technically, do we still have a square root in our denominator?
Yes.
Yeah, because I is still the square root of negative
Also,
1.
now we have an imaginary number, which makes it really
Wait,
hard.
now can we square both sides? That we get.
You can't square both sides because we're looking at a section of fraction.
Yeah, but we could multiply by 1. The question is, which 1 do we want to multiply by to get rid of the I in the bottom?
7.
Not 7, but close.
So we need to choose both. Can you multiply the top and bottom by I?
Yes, how come we can multiply top and bottom by I? Because what does I squared give us? I squared is going to give us negative 1, right? Because that will move us out. So let's do that here. 3 times I is 3i. On the bottom, it's going to be 4i squared, which will just be negative 4.
I was really wrong.
You were, because 4 plus 3 would make 7.
What else would I have said?
Okay, are we good? So there it is. We're trying to get a real number in our denominator. That's the whole issue here.
Yeah, but if you multiply it by 0, doesn't it just all go away?
Exactly, so
So
it
in
technically,
the world, we always mark on this new
It's dividing by 0.
Wait, can't we multiply by 0?
No, cannot divide by 0 because 0 over 0 is called an indeterminate form and it's not 1. So 7 over 7 would be 1. 12 over 12 is 1. But 0 over 0 is a fun little number to do.
Just one slide.
On the term.
Okay, class, let's go with it. So A. Whoa. Come on. There it is. A. Can you simplify for me? Let's do one example. Now that we kind of got the concept here. So I say 6 over 7i. Can you guys simplify that? We'll start off simple. We do get complicated here just a bit. So what is the one that we multiply by? I is cool. So I on top, I on the bottom makes 6i on top, makes a 7i squared on the bottom, which just becomes 7 times negative 1. And real quick here, another thing is we don't like to leave a negative on the bottom of our fraction. And so the negative has to either go in front of the fraction or we bring the negative on top. So there's your two different possibilities right there. Get that negative in front or get that negative on top. Okay. Boom, 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 boom. B. How about something that looks like this? Ah, that'd be fun.
But wouldn't it be? Oh, no, that's different. No, for the negative 6i over 7, what's the negative on the bottom of the 7?
The negative was on the bottom with the 7 first, yeah,
You
and
can
that,
just switch it.
and then for negatives on the bottom, we can move it out in front, or we can move it to the top. Only thing is, hey, when you move it to the top and you have like 2 or 3 numbers, right? Then that negative has to go in each one of them, right? You can't just say, yep, that's cool too. All right, guys, real quick here. How do I get this guy to be a real number? What should I multiply 1 minus I to give me a real number at the end? The conjugate, absolutely. That's why we studied it. No way, that's so cool. So the number that I want is 1 plus I, 1 plus I. Okay, a little bit of work. I'll let you guys try it. Go for it. I mean, there's some people that are kind of bring it in by osmosis, right? Like, oh man, I'm going to get this. I'm going to get to homework. It's going to be easy because they just.
What are you looking at?
Okay, a little bit of work here. Let's see on the bottom. And if you want to add extra parentheses in here, that's fine. But I think we already have, oh, one second, let's put this equal sign on top. This is going to be what? 1 squared, is that right? Plus 1 squared. Everybody good there? That one comes over here. Remember that little formula that we used for multiplying complex conjugates? And there's technically like a little one right over here. So we bring this one down. So everybody okay, this just be a 2 on the bottom. Now the top is going to be fun. That is going to be the FOIL method here. So we've got to do all of it here. 6 times 1, 6. 6 times plus I. Negative 7I times 1. Thank you. And let's see if we can do this the quick way. Negative 7I times I. Positive, everybody okay with positive 7?
Look at all these sevens. Happy is a strong word.
Negative, so it's 13 minus I.
Oh,
13 minus I. Okay, and then let me just check something out. Okay, so one more little thing here. You guys might notice in the textbook, and this one does it. Class, do you see that number there? That is like a single number, right? Because it's written as one big giant fraction, right? The only thing with us is complex numbers should be written as a real part and then an imaginary part. There's like 2 parts to this piece, right? Landon, question?
Would you write it as 13 over 2 minus I over 2?
That is perfect. Actually, 13 over 2 minus I over 2, right? You got those 2 different pieces there. Always written as 2 separate numbers because they're actually 2 pieces of a number put together. They're not a single number. Okay, are we good there? Boom. Okay, and then let me give you, let's see, do we have time? I think we have time for, nah, I'll let you guys do that on homework here. Okay, jump. So now, thanks, Camille. Exercise 7, perform.
It says exercise 6, not 7.
I can't. Yep, need to retire. I start mixing examples around. Perform the indicated operation. Boom. Okay, so now let's get a little more complex here. This one, maybe A. 2I over 2 plus I is being added with, oh man, that's fun.
Oh, and let me know when you get the answer.
Oh, that's right. If we do that, we're going to get a real number, right?
No, because we still have, oh, no, you're right.
So let's go with, I see 2 fractions that need to be added together, right? Therefore, I need to have common denominators here, right? So in this case, I'm going to have to need a 2 plus I and a 2 minus I to form my common denominator. 2 plus I over here and a 2 minus I right there. Boom, boom, boom. So that means I need a multiplier of 2 plus I here. Talk to me, see if that makes sense. On this side, I need a multiplier of 2 plus I.
I don't.
A pencil. All right, let's see. I'm going to keep this as 2 plus I just for a little bit longer. Eventually, I can multiply these guys out, but how about this? Let's multiply this out. 4I minus 2I squared. Can we put a plus 2 already here? This will be 4I right over here. This will be 2I times a negative I makes negative 2I squared, so plus 2.
Did you see that
The
too?
5 multiplying in gives me a 10 plus 5i.
Yes.
Almost at the end here, almost at the end. Oh, let's multiply these guys together now.
Remember? Yeah. Uh-oh.
Tell me if you guys agree. I should have a 5 in my denominator. Is that true? 5, 5. All right. On top, I have, let's see, 9i. Nope, I have 12 plus 9i. Awesome. That's cool. Yeah. You did it by, yep, that's fine. You still kept them separate from each other. That's cool. All right, and then we do separate them at the end. So here it is, 12 over 5 plus 9 over 5i.
I got that.
Right there.
Wait, you can bring the I out like that?
Say again, Owen?
You can, when you have 9i over 5, you can bring the I out, a fraction like that?
Yeah, let's see, it's kind of like the same thing as this right here.
Oh, that makes
3.
sense.
You can't do that.
Those mean the same thing, there's still a multiplier to it. Okay, let's move on as we put things together here. So how does this help us? This helps us with the quadratic formula.
Oh, wait, I love that.
So exercise 7 finally
Oh, I
here.
only like doing it where I plug in numbers and stuff. Well, no, they actually do it like the useful math even. I don't do anything useful. Well, that's what you said.
Use the quadratic formula to solve.
Well, no,
She's always right.
it's either 7, 4.
All right, for these guys here, we always, I mean, it says use the quadratic formula, but whenever you have a polynomial in front of you, we always just check with a quick to see if we can factor, that's all. So we're seeing x squared plus 6x plus 10, just a quick jot in your head. Can you factor this guy down, yes or no? Yeah, because 10 would be 5 and 2, right? If it was a 7x, it would work. Or if it was 10 and 1, which was 11x, it would have worked. But not 6x. We're
How
good?
about we erase the 6 and then put it in the 7?
Nah, how about we use the quadratic formula? So let's go with it. It's negative b, right? Plus or minus. So just to remind ourselves of the quadratic formula.
Oh, with that trap, you're giving us I in here anyway.
Say again, Abe.
I said you're giving us a negative in the radical with the trap. It just
That's
doesn't look like there's gonna be any imaginary number.
And so that's the other part is when we start using quadratic formula, actually it kind of works backwards. When Dr. Cardano was using the quadratic formula, he would get these negatives inside the square root. And so for him, many times, well, mathematicians of the day would just cross it out, say no solution to be done, right? What he did is because he was not a trained mathematician, he was a medical doctor that did math in between patients because he thought it was kind of funny. Whoa, what happened here? Did I just do that?
Where are you guys getting
He just stuck that in there here. So tell me, 36 minus 4 times 1 times 10? All over 2 times 1?
So 6 for
Okay, you guys talk to me. Do you guys know where all those numbers came from, first of all? Boom, boom, boom. And do you guys have the same numbers as me?
That's a 10, not a 6.
That should be a 10. I'll write it as
Hey, look, now
10.
that makes sense.
No, it doesn't, man. You have a negative square root.
So this will be 36 minus 40. So Dr. Cardano and mathematicians were faced with this right here. That is it right there.
No, I get.
So the question is there an answer here or do we just chop it and say no solution? And so this, yeah. So this little piece,
That made more sense now. No.
let's split it off into different pieces. And simplifying it down would give us,
Yeah, actually doesn't.
With the square root of negative 4 is equivalent to 2i.
uh-huh.
I told you. And then I told you I was wrong.
Wait,
So I told you the right thing and then I told you the wrong thing. That's my bad.
Owen,
And this would be -3 plus or minus 1i or just I. Are we good?
why
Square
is
root of
it?
two.
Cool. Tristan, question.
Could you have the I on the -6/2I?
You would have it like this right here at first, right? And then you do have to split these off into two different fractions.
No, I know, but you have to remove the I from the
Oh yeah, sorry. Like if you have it like this initially, like this. Yeah, that's fine, perfectly fine.
Why do people 2I not 4? I thought that's very thing.
Because you still do the square root of 4.
You can break it into the square root of I, the square root of -1 times the square root of 4, which is 2, and then that's 2I.
Perfecto here. It's this multiplied by this, which then becomes, technically becomes that right there. That's not a good way to write it though, because we can't split a negative from multiplication. Okay, and should we do one thing? And one more thing. Exercise 8. We go full circle
See, I
here.
like both numbers and other things with the same thing and then adding them together and then getting an answer.
Simplify.
No.
Okay, so here's ourselves a little problem.
I don't know.
Dot is a multiplication dot. So the square root of -5 multiplied by the square root of -10. We got ourselves a little problem. Let's go back to algebra 1. If you guys remember the rules from algebra 1, it said this. It says you can multiply these guys together as long as they are both positive. And you should have this little disclaimer that said this right here, that A and B are both bigger than 0. So you cannot multiply negative numbers inside square roots to give you a simplified square root.
Oh, and did I do the wrong stuff? Oh.
Oh, so then let's do this here. So I does not, the 5 is not a perfect square, right? But because it's a negative, can I still take out an I?
Yeah, you worked on I. That's not.
Absolutely. I goes on the outside, by definition. And then the 5 just still stays inside there because there's no perfect square. We can do the same thing for this one. We can say, okay, that was a -10, so the I goes on the outside, the 10 stays on the inside. And now are the square roots positive? Absolutely. But I times I is I squared. 5 times 10 is 50. And let's simplify. -1. What's the square root of 50?
Well, I was kind of close with not the last.
I don't know the square. I don't think so.
25 times 2 and 25 is 5 squared, so you can go that high. Oh, that's what I,
Perfect, yeah.
yes, that's exactly what I got. Oh.
5 root 2 and -5 root 2. There it is. Looks kind of funny at first though, right? But with the negative side, and notice the negative still stays there, right? Negative becomes the negative on the outside at that point. Okay, let's see, one more. That's B. The square root of -25. Oh, there you go. How about this? How about this? The square root of -25 being squared.
Cross those out and it's just negative.
No.
Interesting. So from algebra 1, we have this little rule that says if I have this and this, I can cross these out as long as x is greater than 0. So all these rules.
You can just take the I out.
Yeah.
So all these rules.
You get the same answer, you just have to do it the long way. Right?
That's annoying.
Again?
Can you just take the I squared out?
No, you have to turn it into 5i
Oh, wait.
and then
I get
square it,
set.
which is 25i squared, which is negative 25.
Thank you. Isabel's correct. Let me say it in not so aggressive tone. 25 is a perfect square, right? So that goes out. And then the I goes out because it was negative initially. And then
Oh, hey, wait a minute.
we
Yeah,
multiply this out
Oh,
and we get ourselves,
I got the answer a while ago. I just now
Wait,
came to the
but-
conclusion.
What?
Yeah.
huh?
My brain was.
So-
You technically get that if you do the thing with the thing, and then you
What
could
do you
just do
cross
less
out?
steps.
Yeah, but you get this little negative on the outside that you don't normally get.
No.
Oh, wow, does it work? Does it still work?
I was just gonna literally cross them out, just have negative 25.
Yeah, that's what I did.
That's interesting.
That's what you want to do, but you can't say extra
Exactly,
denominator.
so
Same
extra
thing.
step.
It's still the same. Cool.
Wait, so can you technically do it?
You say you like it or you
Don't you Algebra 1 rule, because Algebra 1 was a simplified version of things, right?
Oh.
But with this one right here, with the negative, you could still have it, you'll still have your negative. So then this rule technically can disappear on us
I
now.
really just wanna go back. to
Whoa.
So we have just advanced Algebra 1. How about that?
That's.
Whoa.
That's super slick.
Doing that within the-
Okay, guys, that is it for today.
Big brain.
Yep.
Oh,